In the earlier class, we studied about the conservation of linear momentum. Okay, that is because if there is no what the Newton's second law states is if if the rate of change of momentum, the external force acting on a body or even a system is equal to the rate of change of momentum. Suppose we decide about the isolated system. An isolated system is what? Where there is no external force. Okay, what do we mean by system? System is what? Where there are many particles will be there, many bodies will be there. They all together. So something like that we found when a firecracker bursts. Okay, and all the particles are being thrown out in all sides. Okay, these all are basically system. Okay, so the total momentum, because there is no external force acting on the initial the firecracker, so the total momentum will be always constant. Linear momentum will be constant. Okay, so that's what the conservation of momentum. And then we saw about the free body diagram, how to get the acceleration for the pulleys and different, not the pulleys, anything. Okay, in a free body diagram is whenever I want to find out the acceleration of a certain body in a system, all you have to do is take out the body separately and try to find out what are the forces acting on it. Then you can find out the final acceleration or the motion of it. Okay, so yeah, what I was telling is fine. What else we see in mechanics? Normally in our day-to-day life, what we see in mechanics is the motion of the bodies. Okay, it may not be a single, it may be a system of bodies will be moving around, and what usual common thing happens is they collide each other. Correct. For example, take out even when you're going when you playing, what you're going to do, you kick a football. That's a collision, right? Your leg is hitting a football, or you're playing a cricket. The bat, you're hitting the ball. That's also a collision. So they all collide each other. Okay, so you have to deal. The physics basically all the bodies moving. When you express them in mathematically, then it becomes the mechanics in physics. Okay, fine. So this particular part, collisions, is very important because we see collisions everywhere. And we have to deal in physics, how am I going to understand the collisions? Okay, so for example, as I told you, this cricket bat and the ball, and then the two balls, when the ball bouncing on the ground, you drop a ball, the ball bouncing on the ground, okay, or otherwise here everywhere there's a force acting because there's a gravitational force acting, so there's an external force. Otherwise, if you want to, let us consider the case of when there is no external force acting on it. That means isolated system. So one sort of isolated system is what? A gas in a container. Okay, so what happens? You have a container. Okay, you have a container, suppose a closed container, and there are the molecules of the gas. They're not going to be stationary. Am I right? They all move each other. When they move, they keep colliding with one another. But is there any external force acting on it? No force. Okay, now you can say now the gravitational force. But of course, the gravitational force is very weak on the molecules because the molecule mass is very high, very small. Okay, so we can neglect the gravitational force, or you can take it to the space. And there also they all will randomly, there's no force acting on it. They'll be colliding. So what happens is, so this type of thing. So when the Newton's second law says, if there is a force, there will be change in momentum. And if there is no force, there will be no change in momentum. Okay, that means the momentum must be conserved. So now when I say a system, when I say individual particle, is the momentum is conserved for individual particle? No, because after they collide, they change the direction. Correct. So now as a system, I find there is no change in the momentum, but individually, the momentum will be changing. Okay. So then one of the common way how this momentum changing is by the collision, because they change when they collide. Correct. So let us deal with the collisions. Again, for an isolated system. When I say isolated system, I am not going to have any force. So when you don't apply any external force, and so the system, the total momentum has to be conserved. Okay. And even though total momentum is conserved, the individual bodies, they are going to collide with each other, and there will be a change in the momentum of the body. Okay. So one simple example I can give you is, you must have done some of the you have seen some in science exhibition, you have seen some demonstration for that also. So what I'm saying is, I'm saying there's a platform, frictionless platform, whatever you say, or I'm going to say there is a body and there's another ball. They both are moving at a constant velocity. So let us, this call we as a u1, maybe this is going at a u2. So if u1 is larger than u2, so it go and collides. Am I right? So it collides. So now, is there any force acting on it, the system?
Only the first.
There's a force? Is a force?
Force is on there.
There is no external force. Okay, so in this system, if I see, there is no external force. So the total momentum has to be constant, right? So what happens? So it starts like this. So after some time, they both will collide each other. Okay, they'll collide each other, and then after collision, so this ball may move faster with a velocity v2, and this may move slower, whatever we don't know, with a velocity v1. Okay. So in this process, if you say before collision and after collision, the total momentum has to be conserved. That means what? The total momentum. Here initial momentum is what? If this is a mass is m1 and if the mass is m2, of course the mass is not going to change. We will come to there. It will change at some point. Okay, means it won't remain as a single mass. Let us see that. I will come to that. m1 and m2. Okay. So now the initial momentum, what is that? Your m1 u1. That's the momentum. This momentum is plus m2 u2. The final one, what happened? m1 v1 plus m2 v2. So they both will be conserved always. That's what it says. So m1 u1 plus m2 u2 should be equal to m1 v1 plus m2 v2. So why this has to be equal? Why this has to be conserved? That's what Newton's second law says. Correct? Because there is no force I'm acting. No body is accelerating. This is also not accelerating. This is also not accelerating. They are moving at a constant velocity. So that means there is no external force applied on it. But when they both interact, there is a change in momentum. So individually when you see the body, there is an external force acting because this mass is colliding with this. Okay, but when I see as a whole system, I should see there is no change in there should be no change in momentum because there is no external force acting on it. Okay, so therefore no change in the momentum. My initial momentum, the total momentum of the system before collision and the total momentum of the system after collision, they has to be always same. Okay, this is a conservation of linear momentum. This can never be violated. Whenever you don't apply any force, this has to be always equal. Now the question comes is, well, so when I collide, so now let us say this is a momentum. Now let me speak about the energy. Okay, so what happens? So now let us speak about, try to see the energy of the particle, of the bodies, colliding bodies. Okay, so let us see. So what is the initial total kinetic energy? This will be half. What is the kinetic energy for this? 1 u1 square, and this will be, okay, the total kinetic energy is this. And now here this will be half m1 v1 square plus half m2 v2 square. Now the question I'm asking is, will this energy be conserved? Will it be conserved?
No.
Why not?
Because the values will be different.
So what? I'm adding up. Now the question comes is, of course, there are times it can be conserved There are times it won't be conserved. In the picture what I have drawn, you can see it may be conserved. Because what happened, if both the bodies, they collide each other and move with the different velocities, and if in this collision, okay, there is no heat produced, no deformation, the energy is not used anywhere else, that means from the conservation, energy has to be conserved. Am I right? Energy can neither be created nor be destroyed. So if in this collision there is no sound, okay, sound is a vibration, it is created vibration, that also takes energy. If there is no sound, if there is no heat produced, there is no deformation, if nothing has happened, that means the energy has to be conserved. The energy cannot decrease. At that time, these both energies has to be equal. Correct? That means what? When there is no deformation, when there is no change in, when there is no release of energy in the form of heat or sound or whatever, when there is nothing like that, then this two energy has to be equal. So the kinetic energy will be conserved. Now, on the other hand, if these are the moving droplets in space, water droplets in space, you've seen this International Space Station, the droplets will be looking like a ball, correct? Suppose if these two droplets, this is one big droplet, it's going and it is hitting. So will it bounce back and go? So they will become a single. Okay. Now when they become coalesced into a single big ball. Okay. So now can you say at that case, will your kinetic energy be conserved? Why? Because some of the energy has already gone in this interaction. They become one. Okay. Some molecular interaction, everything is happening. Okay. So similarly, other simple thing is, okay, one of the thing what they given in your book also, they given. Okay. See, for example, so there is a wooden block and you are having a gun, okay, and you fired a bullet, the bullet stuck up in the wood and the wood is moving or carrying the bullet. Okay, so now, well, after firing the bullet, let us call the initial force is being applied. Now the bullet, there is no other force happening, so the bullet may move with a constant velocity. Very high velocity, but it's a constant velocity. There is no acceleration. Because once the bullet leaves the gun, there is not going to have any more acceleration. Am I right? Because up to here, whatever you say, your explosive or the spring action, that will give a force on the bullet. Once the bullet leaves the gun, then there is no force. So the bullet will start moving with a constant velocity. Now I am taking at that point. The wood is at rest. So the system is an isolated system. Once the bullet is moving with a constant velocity, the wood is rest. So there is no external force acting on it. So it's an isolated system. Now, so of course the momentum has to be conserved. Okay. So now when the bullet hits the wood block, the buries into the wood block and carries the wood block ahead. Okay. Of course, in this process also your momentum has to be conserved because that's what Newton's law says, because there is no external force acting on it. That is a fundamental. Okay, so momentum has to be conserved. Now the question I'm asking is, will the kinetic energy be conserved here? No. Why? Because when the bullet hits the wooden block, some energy is released, okay, in the form of heat or whatever. Okay, what happens is, in general what he says is, whenever the body moves, when the body coalesces into one, when they move as a single object. Okay, so initially what happened? So now initially the bullet was having a small mass m1, and this may have a mass capital M. Okay, it moves with velocity. Now finally when it's moving out, the mass of the body will become m1 plus m. Correct? So total mass is going to move. Okay, so these are the two types of collisions we can see. Am I right? In one collision, most of the cases, suppose the two glass balls, marbles you are doing. Okay, so their collision, they won't, you must have seen this demonstration in your science exhibitions. Something like this, and they have a marbles here. Have you seen that? So you lift one marble and drop it, one marble will go up and come. Take two marbles and drop it, two marbles will go up and come. Okay, and this is possible because, of course, there will be some energy released in the form of sound or heat or something, but they are very small. Okay, this is possible because your this collision, the kinetic energy is almost conserved. Okay, the kinetic energy is almost conserved. In the place of glass balls, you put sponge balls. Will it happen? No. Okay, or any even soft rubber balls, they won't work as a glass ball. Okay, they won't happen like this. So this is the one types of collisions where we see the kinetic energy will be conserved, and there's another type of collisions we see where the kinetic energy is not conserved. Okay, because kinetic energy will not be same because some energy is being released in some other form. So that means what we say in a collision, so what we have is, then we see a collision. In a collision, the momentum will be conserved. And the other thing is, and then when I get back to the other one, kinetic energy, it comes to two forms. Okay, that is, it will be conserved or non-conserved. Got it? So this gives rise to two types of collisions. Correct? In one collision, it will be conserved. Another collision, it will be non-conserved. And then we call, so whenever the kinetic energy is conserved, you call this collision as elastic. When the kinetic energy is non-conserved, you call this as a inelastic. Okay, so now you understood what the meaning of elastic and inelastic collision. In elastic, so both the collisions, your linear momentum has to be conserved, but the kinetic energy is not necessarily to be conserved. In a kinetic, so if your kinetic energy is conserved, then you call that collision as an elastic collision. When the kinetic energy is non-conserved, we call that as an inelastic collision. So elastic collision is an idealized one. In reality, you never find 100% elastic collision. The reason is, any body colliding, if there's a release of energy in any form, even a glass balls are supposed to be perfectly elastic. Okay, more closer to elastic, perfect elastic bodies. Okay, even a glass balls, when they collide, even they are not conserved. The kinetic, not a fully elastic collision, because there's some sound is coming up. Okay, so you drop a glass marble on the ground, it comes, hits, and come back. If it is a perfect elastic, okay, so you will end up and reach back at the same height. Okay, since there is a release of some of the energy in the form of one, it won't reach at the same height. That comes from the conservation of energy. Okay, so this is what all about here. So that's what, for the perfect elastic, what happened, you take one ball and leave it, the same force will be applied here, the ball will go up and come here. Okay, in this system we will do. Okay, fine. And here all the gravity is acting, so this won't be, you can't easily consider, when I take up a ball, you can consider that as an isolated system, because you are already giving a force. Because whenever I am going to drop the marble, it's not going to have a constant velocity, because of there's acceleration due to gravity. So force is always acting. So this is not an isolated system. It's an example I am saying for an elastic. Okay. So when you're speaking about elastic and inelastic collision, often what we see about an isolated system, when there is no force acting on, when the velocity is a constant, velocity doesn't change with time, then the collision can be tagged as your elastic and inelastic collisions we can do. Of course, when you can do it on the force also, and force applied also. But for here, what we are doing is when there is no external force, that is an isolated system, we define the collisions into two types. Okay, so that's what they have written about your, yeah. Okay, simple. Can you tell me about, okay, so for example, the same system we are going to do here. Earlier we had this elastic collision, we said, right? In elastic collision, what happened? What they have written is when the sum of kinetic energies. Sum of kinetic energy. Some symbol is sigma. You know that, right? You must have done in your statistics also. You must have done in your 10th standard. So this is total kinetic energy initial will be equal to total kinetic energy final. Am I right? So in an elastic collision, total kinetic energy initial will not be equal. Can you tell me will it be larger or smaller?
Will be smaller, right? Because energy is released.
So I mean initial
The final will be smaller than initial.
correct. So this will be what? Greater. Am I right? Ke final. Final will be smaller than your initial. Okay. So and that's what it's about. But the momentum will be always summation of your momentum. Linear momentum will be initial. Okay, let me write initial will be equal to summation of your momentum final absorb. Final. Okay, let it linear momentum. Okay, so this is what your about your momentum and means elastic and inelastic collisions. Okay. So let me read this line so you will be able to understand. A collision is said to be elastic if the kinetic energy of the entire system is conserved during the collision along with the linear momentum. Okay, so this is one part, and the next one is if colliding bodies join together after collision, it is said to be perfectly inelastic. Okay, in fact, all collisions we see are inelastic. There's nothing like an elastic collision. Because everywhere in collision, there is some sort of energy is being released off. Okay, so whenever energy is released, the kinetic energy is not going to be conserved. So there's nothing like all collisions in reality are a inelastic collision. Okay, so but what happened when the release in the energy is very, very small compared to the initial kinetic energy. So then even though it is larger, if it is approximately equal, then we can call it as a close to an elastic collision. Okay, you got it? And what they say is perfectly inelastic is what? When both the body join together. They call it perfectly inelastic. Okay, but there's nothing like that. All collisions is inelastic collisions. Okay. If the colliding bodies join together after collision, it is said to be a perfectly inelastic collision. Okay. In other words, the colliding bodies have a common final velocity after a perfectly inelastic collision. As I said, this one, they have a common velocity, both of them. Okay. Being an inelastic collision, obviously there is a loss in the kinetic energy system during the perfectly inelastic collision. In fact, loss in kinetic energy is maximum in perfectly inelastic collision. Here, almost all the energy is being, most of the energy, lot much of energy is being transferred into the collisions and they get stuck up into it. Okay, so that's what they say. You know, when the wooden block stuck up with the wooden block and move, okay, the loss in kinetic energy is much high. On the other hand, when the bullet pierces through the wood and go, so the bullet will reduce some velocity because it has taken some of the velocity means momentum is impacted on the wood. The wood also will go. So there the kinetic energy won't be that high. So of course that is also inelastic collision. When the bullet pierces through the wood and go, that's also inelastic collision. When the bullet gets stuck up with the wood and then they move, that's also inelastic collision. So the loss of kinetic energy will be maximum when it is stuck up with the wood and move. Okay, that's what they call as a perfectly inelastic. You got it? So that's what they written also here. Okay, so you can write Yeah, they say na, visualize okay, they're in the ball of the same height also, but of course there's a force acting here. The velocity is not a constant, the force will come up. Okay, there's an acceleration. Say okay, and then we will they given something called the coefficient of restitution, and this is important. This is an important. This is one of the very means mathematically. How am I going to define these quantities? I have to define some quantity, and I say depending upon the value of that quantity, I can tell whether this collision is an elastic collision or an inelastic collision. Okay, so there's one more thing which I forgot to tell you, that is what we call as a head-on collision. Okay, anyway, what you know in a head-on collision in your day-to-day life is a traffic when two vehicles hit each other, correct? Accidents. So that is something when they head-on collision. That's you call as your the two bodies collide, like means opposite to. Okay? There's a head-on collision. In physics, that is not a head-on collision because that's same. In physics also, they all come from opposite direction and hit. That's what you'll learn about your center of mass frame. That later on you will do. But in physics, what happened time being, what you have to do is, if there is a collision between two bodies and the velocity, they fall on the same line. Okay, that means a linear. Okay, they're moving on a line, same line. So this is u1, this is u2. When they collide, you call such a collision as a head-on collision. Okay, that is what, whenever the two colliding bodies, they are along the straight line. After colliding, they move along the straight line. The whole trajectory of both the particle before the collision, after the collision, if they all fall on a straight line, one line, so then you call that collision as a head-on collision. It's not necessarily they have to move towards each other. This is moving with a slower velocity. If some other body coming with a higher velocity and hitting, okay, and then this moves with a faster and this slows down, right? Even that is also a head-on collision. Or if there is a body coming out fast and hit and bounce back. Say for example, there is a heavier mass moving slowly at a velocity say u2, and there is a smaller mass. Okay, I'll put it as small m. This is capital M. It's moving with a velocity say u1, and if u1 is larger than u2, this is going to hit. Okay, it after hitting, it may not travel in the same direction, it bounces back. It starts reverse the direction. Then they both are going to move in the opposite direction. Even that's also head-on collision. Okay, means they all are in the same line. Till then the collision happens on a same line, you call that collision as a head-on collision. Okay. Well, how do you relate it with your day-to-day life when you say head-on collision means both of them should come each other opposite direction and collision? Na? So that is something what you call as a center of mass frame. Okay, there is a center of mass, I can say, we will see it later on. In that frame, if you see these two bodies, you will see all this head-on collision will be coming on a straight line. Means all this collision which is happening on a straight line will appear as they both are coming from the opposite direction. Okay, so in a CM frame, they call it center of mass frame. That you will see later on. I think you have that in your subject. As we go, we will study that. Okay, so this is what we call as a head-on collision. So, a one dimension or head-on collision. A collision is said to be head-on if the colliding objects move along the same straight line. You got it? And then, yeah, okay. Straight line before and after the collision. Okay. So, now we will define, after defining the head-on collision, so what we are going to deal most of your, if I say head-on collision, then what it can there be other collision? There's a oblique collision. Oblique collision is what? They won't be on a straight line. Two objects are coming from like this, hitting and going up. Okay, it's a two-dimensional, exactly. It's a two-dimensional collision. That's not a head-on collision. It's an oblique collision we call it. Okay, spelling is what? Oblique. O-B-L-I-Q-U-E, oblique. Okay, or two-dimensional collision is what you said is correct. Okay, so now, so let us come back. So we are going to deal in this whole chapter. We are going to deal only with the head-on collisions. Okay, no oblique collisions or no two-dimensional collisions. Okay, so it is a head-on collision. There's a one-dimensional collision. So we don't have to need the vector notation. All we have to do is a plus minus. Which direction we call it as a plus? The opposite direction call it as a minus. We don't need a vector direction. So that's the advantage of dealing with your head-on collision, one-dimensional collision. Okay, fine. So what we are going to see is coefficient of restitution. The spelling is correct. STATTUY. Okay, the symbol is E. So what coefficient of restitution is? This is a quantity which is going to tell whether the collision is elastic or inelastic. Okay, or I would say, as I told you, there's no collision is to be an elastic. Okay, I'm telling you whether the collision is closely elastic or closely to a perfectly inelastic. So let us try to find out. There should be one number we have to define. So what am I going to do? So let us have the same way. There are two bodies moving at a velocity. Let this be m1. u1 is the velocity. Okay, and this is m2. u2 is the velocity. They collide, and after collision, what they are going to do? They are going to move with a different velocities. Am I right? Of course, the mass will be same. Let us say there's no for a time there's an elastic collision, whatever we call it. So this is going to m1 is going to move with a v1 and m2 is going to with v2. Correct? So this is after collision. So now what we say is, so let us take the relative velocity before collision. So tell me, what is the relative velocity before collision? Can you tell me? Tell me, what is that? The relative velocity between the two objects before collision. What should be?
V1
Hmm.
V1 plus V2, right?
What is that? The V is U.
No, U, sorry.
Will it be plus? The relative velocity will be plus?
Later is minus. U1 minus.
Yeah, you are sitting here. You are in this ball. You will find this velocity of this body going with the u2 plus u1 or slower?
It will be slower.
What it will be?
U1 minus U2.
Okay, maybe u1 minus u2. Okay, u1 minus u2. Correct? Fine. What is the relative velocity after collision? Here, the same thing, na? So it will be v1 minus v2. Then I define the coefficient of restitution E is equal to v1 minus v2 divided by u1 minus u2. Okay, so we don't have to really take about the vector symbol. We'll bother only about the sign only. Okay. Now, this is an interesting quantity. Why this is an interesting quantity is, so let us see. For example, for a perfectly inelastic, what is a perfectly inelastic? When they both join together and they are moving. So, what will be the relative velocity after collision?
Will be added.
I am saying they both are joined together and they are moving.
It will be 0.
Correct? Yes, of course they are moving. Now they both are moving together. Na? So, of course the relative velocity between them is 0. Right? So, then, so what will be E for a perfectly inelastic collision? Tell me. 0. Okay. The reason is V1 and V2 is going to be equal. They go moving together. Correct? They both are equal. So, this becomes 0. So, For a perfectly inelastic collision, E will be 0. Now let us try to find out what will be the E value for a perfectly elastic collision. Okay, so let us see. So for example, now we are going to do for perfectly elastic. Okay, so this is the one extreme. When I go perfectly elastic, it's going to get the other extreme. So depending upon what's my E value, I can say whether the body is close to elastic or inelastic collision. Okay, so how we are going to, let me write it down here, this one. What is the value we have? E is equal to V1 minus V2 divided by U1 minus U2. Okay, so let us take for a perfectly elastic collision. So how are we going to do? So in a perfectly elastic collision, what is that we defined? The total kinetic energy has to be conserved. Before and after collision has to be constant, right? So first thing is momentum will be conserved, correct? So tell me what is the momentum conservation? The same thing what I'm going to. So what we're having is m1 v1 plus m2 v2 should be equal to m1 u1 plus m2 u2. Okay, that's the total momentum. Okay, so and now this is a momentum conservation. Now tell me what is what will be your elastic collision? So kinetic energy also will be conserved. So that will be what, half m1 v u. Correct. Yeah. All the places half will get cancelled off. So this will be m1 v1 square plus m2 v2 square will be equal to m1 u1 square plus m2 u2 square. So let us try to do a jugglery here. Okay. What do you have to do? We have to find out v1 minus v2 divided by u1 minus u2. Okay. Tell me how are we going to find out?
You can take the m1 outside the first equation. You can take the m1 in one side.
Let us take a minus side, my dear. Okay. So from here, let me correct the m1. Let me take all the m1 together on one side. Okay. So that's what you were saying. Yeah. So then what happens? So from here, we can write m1 v1 minus u1 equal to m2 into u2 minus u1. Similarly, from here we get m1 v1 square minus u1 square equal to, tell me.
Above it's empty u2 minus v2.
Oh, sorry. Yeah, what is that? This is u2 minus v2. Correct? Am I right? Yeah. Here m1 u1 v1 square minus u1 square equal to m2 into u2 square minus v2 square. A square minus b square equal to a plus b into a minus b. So this is going to be m1 v1 minus u1 into v1 plus u1. Okay. And this will be equal to m2 into, tell me, u2 minus v2 into u2 plus v2. Okay. So now m1 v1 minus u1, v1 minus u1, m2 u2 minus v2, u2 minus v2. Let me call this as 1 and this as 2. Let me take the ratio of these each other. Correct? 1 or 2 divided by 1. Correct? So this divided by this. So m1 gets cancelled. Correct? v1 minus u1, v1 minus u1 cancels. So what we are going to get? v1 minus u1 will be equal to this divided by this. m2 gets cancelled. u2 minus v2, u2 minus
v1 plus u1.
Correct. Good. Okay. So m2 gets cancelled. This also gets cancelled. What you left over is u2 plus v2. Okay. So now let me take u2 here. So u1 minus u2 will be equal to v2 minus v1. Okay. Actually, I think in an elastic collision, I must have missed the sign somewhere else. Okay, wait. So let us take the ratio of it. So then what happened? V2 minus V. This is V1, na? Okay. So V2 minus V1. V2 minus V1 will divided by U. Sorry. What am I doing? This is V2, V1. Am I right? So V2 minus V1 divided by U1 minus U2 should be equal to 1. I missed the sign somewhere else. There's a mistake. What is this? A coefficient of substitution, E. I missed the sign. Okay, so what it says is this is equal to, I should write negative times your relative speed before collision divided by relative speed after collision. Okay, so there is a negative sign which I missed. Okay, the coefficient of restitution will be minus of it. So what we have is, what I wrote earlier is wrong, you have to correct it. Okay, so E is equal to minus of this. So that's what your E is. Okay, so I missed the negative sign. Correct. Fine. So this is your, remember, don't make this mistake. You have to have the minus. Anyway, this is okay. Because even though you put a minus, what is going to become? So in this case, E is going to be V2 minus V1 divided by U1 minus U2. Correct? Yeah, only the sign changes. Okay, so V2 minus V1 in a perfectly inelastic collision, E is equal to 0. So what happened is, for elastic collision only we missed it. So now what happened? V2 minus V1 divided by U1 minus U2, that's equal to 1. That is nothing but E. Am I right? So what it says, for perfectly elastic, your coefficient of restitution will be 1. You got it clear now? So that says, so all you have to do is, in between two collisions, find out their final velocities, find the initial velocities. So you don't know whether the collision is, you find out the initial velocities, relative velocity, and the final relative velocity, and take the ratio. If the ratio is closer to 1, that means the collision is close to an elastic collision. If it is not equal to 1, okay, if it is close to 0, very small, then you call that collision as a inelastic. Okay, got it? Any doubt you have? Okay, fine. So now, well, they gave one more example. Okay, that is, you can do it by yourself also. For example, what we have taken is, we have taken both the bodies are moving along the same direction. Am I right? You can do it from yourself. The same way you can do it. So what we have, so we took the body M1, which is moving with the U1, going and colliding with the body M2, which is moving with the U2. Correct? After collision, if M1 moves here with V1 and M2 moves ahead with V2, okay, still this will be satisfied. Nothing, because what happened now, your V1 will take the opposite direction. Correct? Earlier we took everything along same direction. We took, this is a positive direction. Now the V1 sign will change. Okay, now the relative velocity between these two is V2 plus V1. You got it? Because what is the relative velocity in earlier case we had? Yeah, the velocity we had is V2 minus V1. Correct? Now V1 is negative. So this becomes V2 plus V1. Okay. Do the whole thing. You will find that for that also this will be the same. Or you take even the head-on collision, coming each other, opposite velocities. Okay, then your U1 plus U2. After colliding going, there also you will find whenever there is a kinetic energy is conserved, your coefficient of restitution will be always equal to 1. This you can do it by yourself. Okay, show it in this is an exercise you have to do. You have to show it when the V1 is opposite direction. You have to show for a perfectly elastic collision, the coefficient of substitution should be equal to 1. Okay? So, and okay, with that I stop. In the next class, we will see about the next class will be, we can see, okay, now I'm giving you a, so now the point is, let us take this elastic collision. I'm giving the elastic collision. I mean the E is equal to 1, or maybe an elastic collision that we will see later on. Okay, E equal to, or maybe elastic or inelastic collision I have given. So E equal to 1. I'm giving you an initial velocities. Now, you have to tell me what should be the final velocity of the bodies after the collision. Okay, so this is what will be the final velocity of the after a head-on collision and elastic collision they are given. I think they are not given in inelastic collision. Yeah, they are given also. Okay, loss of kinetic energy during the inelastic head-on collision. These things we will see it in the next class.